Okay, so now we can finally move on to the parabolic function. Exactly as we discussed the linear function, we will first talk about the parent function, then we'll introduce the parabolic function in a more generalized form and understand what these constants mean and how they affect the shape. Exactly as I said, that we have to understand these things and we have to expand on the parent function because we want to solve much more complicated problems. Right? Things in the real world are not as ideal as theory make it to be. So we try to, and so we're trying to learn it in such a way that we can apply it in real scenarios, right? That's the reason why we have these constants here and this plus q here. It's for that reason. Okay, so the parent function is very simple. It's y is equal to x squared. That's the parent function for the parabola. And so if you put it in functional notation, it'll be f of x is equal to x squared, where x is the input, x squared is the function, and f of x is y. Okay, and so if you put in 1, so f of 1 will be the same as 1 squared. Remember, whenever you substitute to parenthesize, so that'll output 1. If you put in 2, that'll give you 2 squared, which will be 4. Now the thing is with the parabolic function, it's symmetrical about the y-axis. And so we have to put a few coordinates that's on the negative side in order for us to have a full image of what this parabola looks like. Because we'll have the tendency to only want to put points on the positive side. Now with the line you can put points on the positive side because you just need a minimum of 2 and then you can join. With the parabola you can't do that. Because if I put 3 points, then the curve is going to look as follows. Right? But we're missing out the second part of it because exactly as I just said, I gave you a very brief idea of why that's the case. It's because it is symmetrical about the y-axis. And so whatever you have here, you will have here. That's what we mean by symmetrical. It's symmetrical. If I had a dot here, the dot has to go that side. Right? I will elaborate on this more deeply. But what I'm saying is that you need to put a few points on the positive side and a few points on the negative side so we can get the full image of the parabola. Right, so here you'd have f of 0 is equal to 0 squared, which is equal to 0. F of minus 1 is equal to minus 1 squared, which is equal to 1. F of minus 2 is equal to minus 2 squared, which is equal to 4. And so if you look at this here and if you plot these points, minus 2 and 4, minus 1 and 1, 0 and 0, 1 and 1, and 2 and 4, and we join all these points together, we will get the parent function for the parabola. So that's all we are doing, right? That's the parabola in its most basic form. Okay, and exactly as I said that we do need a minimum of 3 points to sketch the curve. Very simple. Now, let's move on to the more generalized form. Exactly as I said, when things happen in patterns, we can generalize it. We want a more generalized formula, right? That can include every possibility in the real world. And so let's say that we are working with the parabola in the real world. We want to say, okay, what is that one equation that can fit every scenario in the real world? And this is how we come down to this formula here. Because in certain scenarios, we could have a number in front of the x squared. In other scenarios, we could have plus something in front of the x squared. And so that's what we are doing, right? We're trying to create a single formula that could generalize every possibility. And then as the years go on, we'll start adding to this formula until we get it into its most broadest form, right? Until we can get it into a form that encompasses every possible situation. Okay, but for now, this is all we need to know, ax squared plus q. So let's analyze the effect of a and q. So now how would we do that? Again, I broke it down into the sign of a and the magnitude of a. So remember, these are numerical values, but we break it down into sign and number because those two things do something that we need to analyze, right? So the sign of a affects the concavity of the function, right? If a is greater than 0, then the concavity of the function is concave up, okay? If a is greater than 0, then the concavity of the function is concave up. So what does that mean? It basically means that the function, in a very simple sense, it curves upwards. In a very simple way, you could think of it like a cup, right? A cup. Can you see the cup? That's the way you can think of concave up. If a is less than 0, then the concavity of the function is concave down. How would something like that look? It would look like this here, like this. Concave down, right? So you have concave up and concave down. Concave up, you can think of the word cup. right? And then with concave down, the function basically curves downwards. Now, I can give you much more formal terminology for this, but for now, you just need to remember concave up, cup, think of it curving upwards, and concave down. Down means think of the entire graph curving downwards, right? That's the way you can think of it. What A does, the magnitude of A stretches or compresses the parent function. So exactly like how we had m, the gradient for the linear function, what A does, it either stretches or compresses the function. If A is greater than 1, then the parent function stretches vertically. That means it becomes narrower. And that makes sense because if I have to have 2 in this function, so if I had y is equal to 2x squared, right? All these values here will get multiplied by 2 for these same x values. And so what will happen is, let me just take a pinpoint and a specific example. Normally on the parent function we have, for f of 1, it is 1. But now if you multiply that by 2, it becomes, for f of 1, it becomes 2. And so for f of 1, it becomes 2, this point goes there. And so what's going to happen is the function is going to look like that. It's going to stretch upwards, right? In other words, it will reach infinity faster, okay? Because we are stretching the graph, right? And if the a values are between 0 and 1, so it's fraction values like 0, 0.1, 0, 0.2, 0, 0.3, 0, 0.4, 0, 0.5, 6, 7, 0, 0.8, whatever the value is, as long as it's in between 0 and 1, all fraction values, then it'll compress the graph, right? So the graph will grow slowly, and so what will happen is it'll be much more compressed and wider, much more fatter in a sense, right? So it'll go like that, stretched out that way. That's how it will look. And so if we have to do this, if I have to illustrate this visually, this is how we'll illustrate it visually, right? There's the function here, here's the parent function. Every time we make the a value in front, the value that is in front of the x squared, we make it bigger than 1, the function stretches, right? It stretches and stretches. So if I have to give this a color like blue, right? See, this is what's going to happen. We do that. Let's take a vertical line, right? Let's take a vertical line and I'll show you exactly what I mean. If we take this vertical line and we place it by number 1, normally, listen to this, normally this line at 1, it outputs 1 on the parent function. But see what it's outputting now, 2. Why is it doing that? Because the values in the front is multiplying it by a bigger number than 1. It's multiplying it, so it's basically a multiplier. So it's making it bigger than it normally would be, right? Now imagine if I put a fractional value like half. Normally it would have been 1, but now where would it be? Where would it be? Like this. Exactly like this. Can you see that? Can you see that? This is what's happening. And so now, normally it's supposed to be 1, but where is it now? At approximately, let's say, half. And so when you have fractional values, the graph becomes wider, fatter. When you have values that are bigger than 1, then the graph gets narrower and thinner. But can you see what we did? All I did was this, vertically. It either stretches or compresses. Stretches or compresses. That's all the value of a does to the parent function. Right, so you can see this. Now, let's go here and read, right? So, these are the basic values of a we should concern ourselves with. Because if a becomes negative, the same values apply, however the concavity of the function changes. Right, so if we look at this, what's going to happen now is, if we take these exact same values, if I take this exact same function, but flip it in the opposite direction. Right, so let's do that, and let me illustrate that to you. Right, and so now if you're analyzing the parent function that has negative a values, so let's say it has negative a values bigger than -1, then what's going to happen? The function's going to reach the negative infinity side quicker. And so this is what's going to happen. It's going to stretch vertically, but in the negative direction. And so that will become the blue function, right? If you use the same vertical line to see how a affects the function and stretches it, let's see, if I put it here on 1, when x is 1, what do we get for y? -1. So that's what the parent function is, isn't it, for the black one? But see what happens when you put a number that's bigger than -1, like -2,5, let's say. Instead of being -1, it goes to approximately, say, -2,5, or whatever the case is, right? It grows faster. It grows faster. It reaches negative infinity faster, right? But now if I put a value like half, so this is the parent function, what half would do is to do something like this, right? It would do something like this. And so now, normally, the parent function at 1, it outputs -1, but now see what it'll output. See, look at this, put the line here, see what it outputs. -half. So it compresses the function, it makes it fatter and wider. But when you have values that are bigger than -1, then it stretches the function. It makes it narrower and thinner because it must reach negative infinity faster. This green function will not reach negative infinity faster because it has to grow for bigger values of x. And so hypothetically, if I have to say like 1000 is somewhere here, if I come down, right, if I come down, the 1000 value will reach the green function first, then the black function, then the blue function. So which is the lowest? The blue function. So the blue function is getting faster to the negative infinity side. Can you see that? Think about that. If I have to continue these lines down here, and I'm at 1000 for x, the green, it'll first come to the green function, whose y value will be somewhere here. Then it'll come to the black function, whose y value will be somewhere here. Then it'll come to the blue function, whose y value is somewhere here, closer to negative infinity. I hope these visuals help you understand the effect of a, right? That's what we are learning and how a affects the function. Right, so now we understand a completely. We get the idea now. Concave up if a is positive, concave down if a is negative. If a is greater than 1, then it stretches the function, it makes it narrower, right, because it reaches positive infinity faster. And if it is between 0 and 1, so fractional value, then it compresses the function, right, because it gets slower to infinity, right? Because think about it, if you had half, then all of these values here will be multiplied by half. Okay, so let's do this. Let's view this idea from a practical sense. So let's say on the x-axis we have time, which is in seconds, and on the y-axis we have position, right, which is in meters. Then we had two people stand on the top of a roof that is 5 meters high and throw a ball to the floor. And this is the path. So as the time progressed, this is the path that the ball took. So from here, the ball went here. 1 second, it was there. 2 seconds. Say approximately 2.5 seconds, then it reaches the floor. The second guy takes the same ball, throw it from the exact same height, but this is the path it takes. So it's in 2 seconds or in 3 seconds, it progresses and it looks as follows. Then approximately 4 seconds, that's when it reaches the ground. Now, if you look at this, right, we said that this is 5 meters high. If you look at this carefully, right, you can see this, and this is an extremely powerful way of analyzing functions. If you look at this function here, this green function, right, this is what's going to happen. I don't even have to know anything about the equations, right, but it's good if I do. So let's give these functions equations, right? So let's say that I call this here minus half x squared plus 5, and then the black function, we call it y is equal to minus 1 over 9 x squared plus 5. What you would notice is this half here is bigger than this 1 over 9. And so what's going to happen is that, watch it, just look at this, look how brilliant this is. If I continue this function down here, which function do you think is going to reach infinity faster? It's this one. It's this one. Because the a value is bigger than this a value, right? So what we're saying is the bigger the a value is, the faster it gets to infinity, right? This here converts to 0,5 or minus 0,5. This here converts to minus 0,1 recurring. And so which one is bigger? It's the minus half. The half is bigger, and so it's going to get to infinity faster. And so if I choose some x value, like this x value here, and if I come down, this function is at minus whatever, but this function is still at a positive. And so if you continuously go to the right, this function is going to get to infinity, this green function is going to get to infinity faster. And so this is why we can say, we can make a lot of, or deduce a lot of information from this. We can say that this ball here was traveling faster than this ball, because it reached the ground first compared to that ball, right? All else equal. Let's not make it complicated, but I'm just saying, you can see how purely based off the concavity, we can make these conclusions. Okay, and so let's say that the ball was the same weight and all of that. If you don't, let's from air friction, ignore air friction and all of the other variables. I'm just saying, look solely at what we have. Just the ball being thrown from the top of the same building, which reached the ground faster, will be the green graph. And so you don't need these visuals. Just basically looking at the concavity or the values of a, we can make these conclusions. That's the power of functions. And that's the power of just looking at the concavity of the function, right? So that's in a practical sense what we are looking at. Now, if you look at the effect of Q basically shifts the function vertically. And so if I take this exact same example here, if y equal to x squared, exactly as we discussed the linear function, if y is equal to x squared, is the parent function, and if we just did this y is equal to x squared plus 1, then y equal to x squared is the same as y is equal to x squared. And so what we're doing in this function is we are adding 1 to the outputs of that function. So when this was 4, it was 4, but if we add 1, it becomes 5, right? And so at minus 2, we'll put a dot at 5. At minus 1, it is 1, but because we're adding 1, it becomes 2. So I'll put a dot there. At 0, it was 0, but because we're adding 1, it'll come there. And if you do that to all the points, what's going to happen? It's going to shift the entire parent function 1 unit up. And so we take all the infinitely many points that make up the parent function and we add 1 to it. And so what the Q value does is it shifts the function up and down. So yeah, right. So that's basically it in a nutshell. You understand the parabola in the generalized form. You understand how these values of A can help us in real world scenarios and how we can think of these ideas from a practical sense, right? Just even if you don't have the graph, but see, even if you were given these equations, you need to be able to know how to draw it, right? Because think about it, if you went here and think about this. If you went in here and you put points into this equation like 1, 2, 3, 4, and minus 1, minus 2, minus 3, you're going to waste time, right? That's why you need to understand what these graphs are showing you. Or even if you go and you sketch these graphs and you do something wrong, you should know that this graph here should be thinner than this graph, because this graph here has an A value that's bigger than this graph, right? So it's ways of thinking of it so we can evaluate if our answer is correct. Don't just think of this as it's a burden to know. It's not. It's teaching you something, and that's how you screen your answer. We're getting the same thing, but looking at it from many different angles. That's what we are trying to do, okay? And so that's the power of just looking at A or looking at these Q values and so on. So everything needs to coincide, right? Because with much more complicated examples, you need to be able to screen these things. And let's say that you're not allowed to use a calculator, right? How are you going to do this? You look at just the main points and just get a rough idea of what the graph looks like. And so when you're solving much more complicated questions, you have a visual to look at, okay? So yeah, I promise you, you get quicker with sketching functions, you'll be able to solve much complicated questions faster, right? And much more accurately. That's more important, okay? So yeah, let's look at the components of a parabola. Right, so now we will finally move over to the components of the parabolic function, right? Exactly as we did with the linear function, we talked about the components of the linear function. We will do the same with the parabolic function. Exactly as I said, we give these things names because they are significant to us, right? Otherwise, we would have just called it some random point on the function. The fact that we give it names means that there is some significance to it. And so we need to learn that. Although we have to go in this order, the first point that I want to talk about is the turning point. Because exactly like I said, when we talked about the linear function, I said that the intercepts is the most important point for the linear function. When we talk about the parabolic function, the turning point is the most important point. And so what the turning point is, it's the point where the function's y value reaches its maximum or minimum value. Let me say that again. The turning point or stationary point is a point where the function's y value reaches its maximum or minimum value. And so if you try to think of this from a different perspective, right, this is just beyond the scope of the grade 10 syllabus, but let me just show it to you. If we had a function here and we call that the position and we call that the time, and someone took a ball at the top of a building and they threw it up and it came down, then we can say that this is the maximum position or height that the ball reached. Would you agree? That's the maximum height it reached before falling down to the ground. Do you understand what I'm saying? And so that's what we mean by the turning point. And so this would have been some ordinary parabola. But because we can't have negative time values, that part has to come out of there. So we have to start from 0 going forward. Time can never go in the negative direction, right? And so we can think about the exact same thing about minimum, right? I can think of much more complicated examples, but I don't want to do that now. The way you just got to think of this is that when you have a concave up function, then you'll have a minimum value. Here we have a concave down function, therefore we have a maximum value. And so can you see how much information we can infer just by looking at the sign and the magnitude of A, right? If the sign is negative, it's a concave down, so that means we'll have a maximum y value. And please, let me say this. Whenever you think about functions from the real sense, don't say y value. It's the maximum position. And so when we say y value, you in place of that y value, you need to ask yourself, what is on the y-axis? It's position. And so I could do the exact same thing. I could take a position, I could take a time, right? Hear me out. I could take a position, I could take a time, I could call this n and I could call this t. What am I trying to illustrate here? I am trying to illustrate a quadratic sequence. Now you would have done this at grade 9, right? Briefly, you would have done this, or you should have done that. If you didn't do it, then obviously you haven't been taught correctly. But the way you think of this now is these are position values on the x-axis and these are term values. And so the first term is something, the second term is something, the third term is something. And can you see it's taking on the shape of a discrete function? Why? Because n has to be an element of the natural number set, because it's a position. It can't be zeroed or -1, right? Because we said you can't come out zeroed in the class or 1.5 in the class. It has to be a natural value. And so what we can say is, a question in the exam paper will see what is the maximum value that the sequence reaches. And what's the maximum value? There's it here. Whatever that y value is. But it's not the y value, it's the term value. And this is why in place of y value, we see what that actual unit of measurement is. Here in this case, we're talking about term values. So we'll see what that maximum term value is. Another question could be, what is the position of the term of the maximum value of the sequence? So then you'd come down here and you'd locate it somewhere here, isn't it? And so that's the beauty of this, because now there's so many questions that we can frame around just the turning point. And so whenever you think of a parabolic function, whenever, and hear me out, this is extremely important. Whenever you move a parabolic function, you move the turning point first. Whenever you move a parabolic function, you move the turning point first. Okay? And that's extremely important. That's the reason why when we get to the hyperbolic and the exponential function, where I talk about moving the asymptotes, that would make sense there. But what I'm saying is, this is why the turning point is so important. Because if I'm adding 1, right, let's go back to the parent function. If I come back to the parent function here, right, and if I take out all of this, and if I add 1 to the parent function, right, if you add 1 to the parent function, the way you frame this in your mind is you're taking the turning point and you're adding 1. If you add 2 to the parent function, you're taking the turning point and you're adding 2 to it. Then every other point will move with it. And so this entire function here now will move up 2 units, but it started from the turning point. It's just a way of thinking of it, because the turning point is the most important point. And you'll understand precisely why I'm saying this when we start sketching functions. So don't think of any other point. Yes, every other point is moving 2 units or is moving 1 unit. But the way you're supposed to think of it as if we are moving the turning point by 2 units. I will tell you why when we get to sketching of functions. Okay? But for now, you get the point. That's very simple. So that's the turning point story there, right? Now let's move on to the domain and range. When we talk about the domain is the x values for which the function exists. Since there is no restrictions for x, we can say that the parabola exists for all values of x. So what would that look like? Exactly as we illustrated the parent function, you have a parabola with arrow weights going on both sides. So it shows you that it goes to infinity, positive infinity and negative infinity. There is no restrictions, right? Mathematically, we write x elements of real. But I've just illustrated an example here that you would do at grade 11, where you have a discrete function. So it exists for only natural number values. And so that's the reason why you would write your domain as follows. And then I've also given you an example where we're talking about a function where you have position and time. So you have position and time. And so what would happen here now is you would say that it'll be x element of real. So it can be any real value, right? Because time can be 1.5 seconds, whatever. But x has to be greater than or equal to 0. And then we can go a step further and say that we can't call it x, we can call it time, because now we're talking about time and not x, right? So yeah, we've talked about all of that, and yeah, so that makes sense. When we talk about the range of the parabolic function, it gets a bit more complicated, but it's not very hard when you understand it. Because remember, we just talked about parabolic functions having a turning point. And so that means that there'll be a maximum value that the function exists for, or a minimum value that the function exists for. And so if I just do the 2 illustrations here, see this? This here will be the minimum value the function exists for. And if I do this, right, this will be the maximum value the function exists for. And so the y values will start from here and go lower. Here the y values will start from here and go higher. It will never go below this. It's the minimum, the lowest. This is the maximum, the highest. Cannot go higher than that. So what happens is, we start from negative infinity, right? Watch this. We start from negative infinity. What's happening to the y values as we go from left to right? The y values are growing. It's growing and growing and growing as we're coming from left to right. Eventually it peaks out. It peaks. It goes to the highest value. And then it starts to shrink, shrink, shrink until you get to negative infinity. Here the exact same idea applies. Again, remember we're reading a function from left to right. So if I go from left to right, if we start from negative infinity and go all the way to positive infinity, this is what happens. At the extreme, at negative infinity, this parabola function is at positive infinity. What happens is the function shrinks, shrinks, shrinks. It goes smaller and smaller until it reaches a minimum value. And thereafter, what it does, it grows, it grows, it grows, and it goes all the way up to positive infinity. Now, remember when we did the linear function, it either grew from negative infinity and went all the way up to positive infinity, or it shrunk from positive infinity all the way down to negative infinity. Here now, this is the thing that you need to remember about the parabolic function. It first grows, and listen to this, it grows, right? It remains stationary and then it shrinks. Or it shrinks, remains stationary, then it grows. The point when I'm saying remain stationary where there is no change is called the turning point. That's the reason why we call it a stationary point. An idea that will be extremely important when we talk about calculus at grade 12. So now you can understand I'm making a link here now. With the linear function, it either grows continuously or it shrinks continuously. Here, this grows, it stationary for a split second, shrinks. Here it shrinks, stationary for a split second, grows. Right? That's what we need to remember there. Right, so if you're talking about the range, let's get back to what we're talking about. It will always output a y values greater than the turning point, right? But that's only if a is greater than 0. So if a is greater than 0, the function should take on a general shape like this. And so it will always output y values that are bigger than or equal to the turning point, right? And here, if a is less than 0, that's the general shape, it will always output y values that are less than or equal to the turning point. And so where the turning point is, that's what we need to analyze. And so now if you have to draw the function here quickly, let me show you this. If I have y is equal to ax squared plus q, see, q is what we call the turning point, right? It's also called the y-intercept. So this is the turning point and it is the y-intercept. So if you want the coordinates of the turning point, listen to this, it will be the same as the y-intercept at grade 10. Let me say that again. At grade 10, the coordinates of the turning point and the y-intercept will be the same. I can prove this for you, but you're not ready yet to take that knowledge in. So you need to learn this. Learn this as a fact. Q is the turning point and the y-intercept. So what is this coordinate here? This coordinate here will be 0 and Q. But since it's on the region, it'll be 0 and 0. Okay? If I have to take this out here and do a much more generalized form, if I did something like that, then this coordinate here will be, x will be 0, but y will be q. It'll be the same as the y-intercept. And so when we're trying to write the range for this function where a is greater than 0, then it'll be, the range will be y is an element of real. So the values can be anything, rational, irrational, whatever. But the restriction is that it will never go lower than q. So it'll always be equal to q and higher. So therefore, y will be greater than or equal to q. So it's equal to q and higher, right? On the other hand, if we want to write this in the other way, it'll be like this. So if we have this function looking like this, where a is less than 0, so that it's a concave down function, what's going to happen is, at this point here, it'll have the coordinates 0 and q. Same thing, nothing different. But what's going to happen with the range is now it's going to be y element of real, but y will be equal to that value and everything below it, everything less. So it'll be y less than or equal to q. Right, so yeah, I wrote it here. So let's read this. For the parabolic function, the graph will always output a y value that is greater than or equal to the turning point if a is greater than 0. Right, that's what we have here. If a is greater than 0, then the range will be equal to the turning point or higher, bigger. But if it is less than, if a is less than 0, so we have a concave down function, then the range will always be equal to the turning point and everything below. And so the way I put it here, it's written so perfectly. It's similar to saying that if I input any x value into the function, I'm certain to output a y value that will be greater than or equal to q. Listen to this. It'll be greater than or equal to q if a is greater than 0. Or if I input any x value into this function, I am certain that I'll output a y value that is less than or equal to the turning point. Because here we have a minimum and here we have a maximum. It has to be less than the maximum and it has to be all values bigger than the minimum. Right? These are ways we can frame this in our mind. So if you want to take down this notes, you can do this. Firstly, we write the generalized form and what each part means, and then this can go here. So you can segregate your thinking nice and neatly. So this will go there, and this all goes together here. Right, so take down this here, exactly as I have it here, nice and neatly. Right, so once you have that, then you have everything that you need to know for the parabolic function and domain and range. Okay, and then obviously I've just given you the examples where we have to state where the domain may change and whatever the case is. But the thing that you need to remember is the maximum and the minimum. Okay, if we talk about the intercepts, the x-intercept is the point where the graph intersects the x-axis, and it is the point where y is equal to 0. And the y-intercept is the point where the graph intersects the y-axis, and it's the point where x is equal to 0. Now, this is where things get a bit more fun now. Because when we talk about the intercepts, we can go so much more in depth. Now, for the x-intercept, let's segregate our thinking here again. We have x-intercept and we have y-intercept. We said the y-intercept is the same as the q value. So if I want the coordinate of the y-intercept, I can read it from the formula, and I know it'll be x is equal to 0, y is equal to q. Right, so let's do that here. Right, let's do that here. So we're starting with the standard form. Remember, we're talking about the intercepts. Right, let me just put this down. It'll be y is equal to ax squared plus q. Right, please, you have to understand this. These are very deep topics that we're talking about. Right? Now, the intercepts is a very deep topic because we need to understand it from a very broader perspective. When we talk about the x-intercept, and I want to categorize this in 4 cases, right? The first one is we have the parabola here, right? And we have a concave up parabola. You see at this point here, we have one intercept because the graph is sitting on the origin. So there's one x-intercept, right? If I take this parent function and I shift it down just a fraction below the origin, what's going to happen? We're going to have 2 x-intercepts, isn't it? 1 x-intercept, 2 x-intercept. And lastly, if I take this function and I shift it just a fraction above the origin, we are going to have what? No x-intercepts. And so, how do we find the x-intercepts? How do we find the x-intercepts? How would we do that? Right, that's a question we need to ask ourselves. And so if you're given the graph, y is equal to 2x squared minus 2, how would you find the x-intercepts? How do you find the x-intercepts? It's the point where y is equal to 0, isn't it? So x-intercept is the point where y is equal to 0. Watch the beauty of everything that we're doing now. Check here. If I make the 0 is equal to 2x squared minus 2, right? How do you solve for this? When you are solving for a quadratic equation, we make use of what? The zero factor property. And this is how everything is starting to link now. This is how everything is starting to link. We're going back to solving equations from term 1. Right, let me prove it to you. Let me prove it to you. 1 minute. And there's it here. This is what we call a function. When you add the zeros, does this not become an equation now? Isn't it? And how do we solve? Look at this. We are simplifying and solving. We're solving a specific type of mathematical statement, which is an equation. And how do we solve a quadratic equation? Through factorization. And if we go even deeper, how do we do that? Is by making one side equal to 0, which is already done as a consequence of finding the what? The x-intercept. So we are indirectly using the zero factor property. And so we have to do this question if we have to do this question, then this would be, look at this. This would be divide by 2 throughout, so this will be 0 is equal to x squared minus 1. X squared minus 1. We are dealing with a difference of two squares, because we have a binomial, so we have to make use of the special binomial technique, isn't it? So there'll be x plus 1, x minus 1. The zero factor property states if the product of two numbers equal to 0, then either of those numbers has to be 0. So therefore it'll be x plus 1 is equal to 0, or, you have to use the word or, x minus 1 is equal to 0. If x is equal to minus 1 or x is equal to 1. Right? If you have to do a quick sketch of this function, this is why you have to become so quick with sketching. There's the function here, right? There's the function here. You'll have the parabola that will look like this. That will be exactly 2 units below the origin, because the turning point is there, isn't it? The turning point is here. So the turning point will be 0 and minus 2. Here, this x-intercept will be 1 and 0. And this x-intercept here will be minus 1 and 0. Right? This will be your axes, right? Label your axes, x and y. The name of this function here will be, we didn't give it a name, so we'll just label it with the equation or with the algebraic form, and therefore y is equal to 2x squared minus 2, and this is what we have. Right, so this is extremely important stuff. Extremely important stuff. And so when you start to look at much more complicated examples, having the ability to draw these functions quickly would really dictate how accurate you can solve the question, and if you understand it at the deepest level. Right, can you see why the roots are so important? Now, we call it roots or x-intercepts. So you can see the different cases. You could either get one root, that's if the turning point lies on the x-axis. So write that down. If the turning point lies on the x-axis. You could get two roots if, and this is where it gets a bit more complicated, if a is greater than 0, means you have a concave up function, and if q, listen to this, is less than 0. Let me say that again. You will get two intercepts if a is greater than 0, so it's a concave up function, and if q is less than 0. Because if q is less than 0, if you got a concave up function and q is less than 0, that means that this turning point will come a fraction below. It will be negative. It will come a fraction below, thereby cutting the x-axis twice. Okay? Here you'll have no x-intercepts if a is greater than 0 and q is greater than 0. Very powerful stuff. I can't emphasize this enough. You would probably, I don't even think your teacher would have told you about this, but this is extremely important stuff, because if you look at this here, a is greater than 0, q is less than 0. What should I expect my answer to be? I should expect to have two x-intercepts just by analyzing these values. And you know what, we can apply this into much more complicated real world examples. But if you understand this, then you understand maths at the highest level, right? And then we can go a step further. That's for the concave up. What about the concave down? Right? What about the concave down? So how would that look like? Again, for the concave down function, the same thing applies. If the turning point lies on the x-axis, right? If the turning point lies on the region, then we have one x-intercept, right? Here we'll have two x-intercepts, right? Take a guess. When do you think we'll have two x-intercepts? Right, we'll have two x-intercepts when a is less than 0 but q is greater than 1. Because if a is less than 0, we have a concave down function. When q is greater than 0, the function will move above the x-axis. So it's not equal to 0, it is positive, some positive value. And so even if it's just 0,000000001 above the x-axis, it's just a fraction above it, you will have two x-intercepts. Okay, and when you'll have no x-intercepts, take a guess, when do you think that'll happen? When you have a less than 0, so it's a concave down function, but q is less than 0. So it's not 0, it's less. So it's a fraction below. So the graph won't even touch the x-axis, it'll lie below it. And so however close you want to zoom in there, it'll be negative. It'll always be slightly down. Okay, so I hope you understand that, because these are extremely powerful thoughts. And you can see how we're starting to link it back to term 1 work. And this is like the maths at the highest level. You understand this, you understand maths. And when you get to grade 11 and grade 12, maths will be a walk in the park. So I'm literally linking everything and giving you a complete overview of what you need to know. This is what you need to know. There's no other way to it. Okay? And lastly, we will work with what we call the axis of symmetry. Okay, and then we have the axis of symmetry, right? And exactly as I said, the axis of symmetry is the line that the function is symmetrical about. So the equation of the axis of symmetry at grade 10 will be x is equal to 0, which is effectively the y-axis. Now I'll explain why this is the case, why we say this. But let me give you a bit more detail about the axis of symmetry, right? If you have to sketch the parent function on this Cartesian plane here, right? Watch here. If you have to sketch the parent function. So we know the parent function has the equation y is equal to x squared. When x is 1, y is 1. When x is 2, y is 4. When x is 3, y is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Right? When x is minus 1, y is 1. When x is minus 2, y is 4. When x is minus 3, y is 9. And so what the axis of symmetry does, which is this line here, the y-axis, right? We're supposed to put a dashed line here to represent that axis of symmetry, is it reflects these points about this line. And so what that means is whenever we reflect a point about the axis of symmetry, the reflection is done so perpendicular to the axis of symmetry. So perpendicular will be here, right? There's it here. It's perpendicular to the axis of symmetry and by the same distance. So there's one block here, there's one block in the opposite direction. Let's do it here. This point here will reflect perpendicular to the axis of symmetry, which is here, and by the same amount in the opposite direction. So this point is 2 blocks that way, this point is 2 blocks this way, right? We do the same thing here. It reflects this point perpendicular to the axis of symmetry by an equidistance away from it. And so this point here, these points move perpendicular to the axis of symmetry, but by 3 units away. And so if we join all of these points together, we get the parabola. And so that's what's so powerful about the axis of symmetry, is that we just need to know one half of the graph and we can get the other half, because we know it has to be symmetrical about the axis of symmetry. Now, let me just give you some more information. You see why? Okay, you see why the axis of symmetry has the equation x is equal to 0. X is equal to 0 because the y values change, but the x is the same. And here, the equation of the horizontal axis will be y is equal to 0. Why? Because the x values change, but y is 0. Right? You can think of it like that. Okay, and so that's how we get the axis of symmetry for the parabola. And this idea will become very important when we work with inverse functions at grade 12. Right, so now you have everything that you need to know about the components of the parabola. Right, so now let's talk about the sketching of a parabolic function. Exactly as I mentioned, that when we sketch the parabola, the most important point is the turning point. Then the intercepts come. And so if I gave you the function y is equal to 2x squared minus 2, let's say, the first thing that you need to look for is your turning point. Right? Once you get the turning point, then every other point will become important. So let's look at the turning point. The turning point is minus 2. So automatically, because we have that, the turning point will lie exactly here, right? Then we have a concave up function. So if I just do a rough sketch, the function will look like this, isn't it? And so it's going to intercept the x-axis. Alternatively, what we could say is that a is greater than 0, q is less than 0. Therefore, we have two intercepts, right? Two x-intercepts, because I've already proven that to you. Now, if you have to find those intercepts, how would we find it? Is using factorization and the zero factor property. So we'll say the x-intercept is the point where y is equal to 0. Therefore, 0 is equal to 2x squared minus 2. First factor out in HCF will be 2 into x squared minus 1. Then divide by 2 on both sides. Therefore, 0 is equal to x squared minus 1. Then we have a binomial. And when we have a binomial, what do we do? Or when you have two terms, then we make use of special binomials. So this will be x plus 1, x minus 1, and 0. Therefore, x is equal to minus 1 or x is equal to 1. So that's the x-intercepts. And so if you look here, the x-intercept, one will lie here and one will lie there. And so we have 3 points already to sketch the curve, isn't it? And so that's the reason why all we need is the turning point and the x-intercepts. Now the problem is, if you have the turning point and there's no x-intercepts, then you need to take other points. Right? So that's the reason why I said the primary thing that we need to focus on is the turning point. Okay, yeah, and then if we join all of these points together, you should have a rough idea of what the function looks like. So it should look something like this. Right? Make sure the curve is neat, and you have your arrowheads you label your x-intercept. So this is 1 and 0. This is minus 1 and 0. At this point here, it will be 0 and minus 2. You label your axis of symmetry, where you have to obviously highlight the axis of symmetry, right? So we'll highlight it first, right? We'll highlight it with a dashed line like this. We'll call it x is equal to 0, and then we'll label the function y is equal to 2x squared minus 2. Literally, that's all we need to know for sketching a parabola, right? So the main thing you need to remember is your turning points and your intercepts. If you don't have intercepts, then obviously you take random points. You take maybe 2 points from the positive side, 2 points from the negative side. But if you do have your x-intercepts, then obviously you use it, right? Another thing that you can remember is maybe you can maybe add another point here and here, just for the sake of accuracy, right? Because remember, we just putting these lines here. We don't know if they actually go up that part. Sometimes you could be drawing the function incorrectly, right? So let me show you what I'm saying. If I put in 2 into this, 2 squared is 4. 4 times 2 is 8. 8 minus 2 is 6. And so for 2, you'll get 6. It'll be 1, 2, 3, 4, 5, 6. Right, which is somewhere here. Then we know for minus 2, we should also get 6 as well. What? Because it's symmetrical about the y-axis, isn't it? We have the axis of symmetry, so we don't even have to put minus 2 and check what the output is. We know it will be 6. That's the power of the parabola. And so now, if we do this, can you see? The more points you have, the more accurate it becomes. The more accurate the curve becomes. Right? The more points, the more accurate. Right? You can even do 2.5. You can even do half, and you can keep refining this curve. Because remember, this curve is actually made up of infinitely many points. And so the more points you have, the more accurate the curve becomes. Right? That's literally everything that you need to know about the parabola. This is understanding the parabola at the highest level. And if you watch this video repeatedly and you get the work done and you write the notes and you use the same thinking frameworks, trust me, grade 11 and grade 12 will be a walk in the park. The reason why grade 11 is known to be difficult is because students have a poor foundation about functions at grade 10. And I've mentioned this repeatedly. Function is the most important topic, right? So this is everything about the parabola. We will now move to the hyperbola and the exponential function.